So today we are going to go back to the end of last class, right? So to try to solve that exercise. Have you managed to try it, to do it? Yeah? Yes or no? Or is it worth to go over it again? Yeah. Okay, and then there are a few details that I kind of skip it over, right? That maybe it's interesting to go back to. And then now, since we have kind of lost our fear of partial differential equations, yes or no? Yeah? Yeah, now we look at partial differential equations, we kind of say, yeah, that's manageable. Yes or no? Yeah? So the deal here is that we actually can look at them, and maybe we are not so comfortable with the whole mathematics, like if we are asked for solutions, like analytical solutions, we have no idea, right? But then that's the case for most for most situations, even if you're a physicist or mathematician, right? So most partial differential equations are really hard to find solutions, right? So but the idea is that at least we have some understanding of what each term does, right? So if you want to look at models and interpret models and have an idea of what they do, right? Now we just have to be able to tell what each term does, right? So if you have a term that doesn't depend on space at all, right? So like, so let's go back here to the, I had another note with the solution for the critical path size. Yeah, let me put up here. So for, yeah, maybe it's the other way around, yeah, like this, yeah. So if you have an equation like this, then we know that, okay, this right term here doesn't depend on space, so it means that at each point in space it grows exactly as if this were an ordinary differential equation, right? Just like an ODE, okay? So this is just logistic growth at the locus area. And then I have a term that is the diffusion term that says that individuals spread around in space, okay? Yeah? Yeah, with that, maybe it's a bit simpler to work on this, okay? So, questions, general questions, comments, okay? So let's try to solve the exercise from last time. So the idea was that we wanted to solve this equation here with absorbing boundary conditions. We thought about this, right? Absorbing boundary conditions. And then what we saw in the last class, right? So if we didn't have any growth, okay, the boundary conditions were such that population was leaking out, okay, leaking out, and then we started with some initial condition, some initial population over there. It leads, all of the population eventually leads through the border, and the population goes to 0, okay? But now we have growth, okay? With growth, we expect population to grow, right? Yeah. So maybe this and counterbalance the leaking through the borders, yeah. So let's try to do that, right? So let's see. So so the code is pretty much the same as. Yeah, what is this stuff here? I don't know. I think Natalia is watching us here. I don't know. Yeah, well, I don't know what I do with that. Maybe I can just put hide video. Yeah, like this. Well, not sure. Yeah, maybe like this. Okay. Doesn't bother you too much, right? So yeah. So okay. So the exercise is like that. So we have these parameters here. So R equals 1, GE equals 1, carrying capacity is 10. One thing that is interesting now is that this carrying capacity now is no longer an unity of population, okay? Because now this M here is not population, it's population density, okay? So if I have my X, I don't know, in kilometers, then this density here is number of individuals or biomass or something per kilometer, okay? So this is now all in terms of density of population, okay? And I specify that L, the size of the habitat, okay, are going to go from X from 0 to 4, okay? So that my space has length of 4. And then I ask you to try also with L equals to 1, right? So let's do the same thing that we did in the last class, or almost, okay? I think there was a +1 here. No, not actually, no, it was in here, yeah. So this is L equals to 4 here, and then, oops, yeah, here we go. And then we look at the animation of this after it runs, right? So let me see if there was anything weird going on here. I don't need this, yeah. This in here, okay. So it ran. Now let's look at the animation, right? So I run this, and now I will render the video over here, okay? What was the initial condition? It was with all the population equal to 1 initially, okay, yeah. So density of 1, right? So this is, let's start from the beginning here. So this is the solution, okay? So I start with some constant level here, and then it grows and more or less stabilizes at something that has this arrow shape here, yeah? Okay? And you see that there's more density of population in the middle than at the borders, because at the borders there's a balance, right? So there's population arriving here at the border from the middle, right? So it increases because of that, but it decreases because there's always population leaking through the border. So there's a balance, you see? Yeah? So what happens if I now change L to 1, okay? L to 1. So I have a smaller size of this range here. Right, so let's do all of the, yeah, there's some warning here. That's weird. And now this video over here is, oh yeah, there's something wrong here. Maybe, what can I do here? There was an error in the integration, right? So it says work done. Maybe if I increase the number of spatial, yeah, I think this, no, this didn't help. What is the time here? Maybe if I put h max equal to 1. Let's see, not yet. Oh, now it works. Okay, good. Let's try to do this so we don't take too long. Yeah, it works. Okay. So we have discussed this before, right? So this whole thing of when you have numerical errors, right? So you can see that also because you're using the method of lines, this is essentially solving a system of OGs, right? So you also have numerical errors solving that system of OGs, right? And the method to make that better is the same that we used before, right? So increasing the number of steps that it can do internally and reducing the maximum step size that it can take, okay? Okay, so let's look at the video of the solution now. So it's, yeah, it's a 2 week, right? So, so let me go back a bit here. So where is the bar here? So at the very beginning, I have the population 1, and after a single time step, no, you see that here the population is not 1, is not 0 yet, right? But there's a small population in the middle here, you see? But now it quickly goes to 0, yeah? So you see, with L equals to 1, we still have growth and leaking through the borders, but now the size of the habitat is too small, right? So there's not enough growth to compensate for the leaking through the borders. So the population goes extinct. Yeah? Does that make sense? So it means that actually, at least from the point of view of this model, populations do have a minimum habitat size, right? If, of course, if all of the individuals that live never return, okay? So, so under these circumstances, then, we can look for what is the minimum value for L that enables the population to persist, to not be 0, okay? Yeah? Okay, so let's maybe try a little bit. So let me put just L equals to 3 here and see what happens, right? So I think this is more interesting. L equals to 1 perhaps was a bit extreme. Yeah, so now we see what's going on, right? So it is at first at 1, and then it decreases, decreases. The question is, it didn't stop decreasing yet, right? Yeah? So if we look at the final population here, it is not 0. But is it not 0 because we didn't run for long enough time, or is it not 0 because it's going to stabilize at a small population? Yeah, so that's the question, right? So we can just go back here and run for a bit longer, yeah? So instead of running only until time 20, I will do it until time 200, okay? Let me take larger subsizes here, okay? And now let's see this video once again. Okay, so it's the same solution, but now for a longer time. Yeah, so yeah, this is going to take a bit longer. Yeah, it looks like it is going to 0, right? Yeah? Yes or no? What do you think? Yeah. Looks like it's going to 0, right? So, you see, this is kind of hard to do by looking at videos, right? It takes a long time to watch each video and then judge if the population is into 0 or not, right? So instead of looking in that direction, right, in terms of the density and so on, right, we're instead looking at the total population, okay? So what is the total population? Is the population sum over the whole space, okay? How do you do that, right? So if you had for instance, here we have n equal to 50, to 100 here, okay? So if I go here and I say, okay, my u here at the end, right? I can take this at the end here, and I can look at what is the final solution here, what is the final population, okay? And I have a set of values over here. Here it's kind of all the density is close to 10 to minus 9, 10 to minus 10, yeah? If I just sum all of these values, right, this looks like the total population size, yeah? If I just sum the populations on every point, yeah? Yes or no? Yeah? But then, but these are densities, right? So if I divided my space instead of 100 points, I divided them in 200 points, these values they would still be the same, yeah? Because this is the density, okay? So if I divide the habitat in 200 instead of 100, I come to the conclusion that I have double the population. That's not right, yeah? That's not right. Do you agree? Yeah, so what we have to do instead of just summing over the values of u, okay? I have to integrate over the values of u. That is a little bit different because it takes into account that actually the spacing is relevant, right? So let me show you on the board quickly what I mean by that, right? So we actually want to take total population of a function that is a continuous function, that is u, okay? So this is x, this is u, and I have something like this, right? So the function is like this, okay? But we don't have the function itself, right? So what we want is the area here, okay? What we want is this area here, yeah? Does that make sense or not? But we don't have the function itself. We have some points, okay? We have this point, 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 and this point, and this point, okay? Then what can we say? Okay, if I just sum them, I have to be careful that this actually corresponds to kind of some, we can approximate this by some rectangles over here, okay? Something like this. You see? So if I just sum all of the values, I have to then multiply by the size of delta x. Yeah? Okay? So we can just sum the values and multiply by delta x. Okay? So this is one way to calculate the total population. Okay? There's a better way to do that that usually gives us a better approximation for this integral, is that instead of assuming that these are rectangles, I can use trapezoids. Okay, so instead of looking like this, yeah, let me draw another one. Yeah, like this. Let me put also less points so I don't have to draw too much. Yeah, so instead of thinking like this, I think, okay, this is, instead of saying that each point represents a rectangle, I say that this represents a trapezoid, okay? So I connect them with straight lines, okay? Yeah, I think I need also points over here, yeah. Yeah, and this here is also the trapezoidal rule, okay, to integrate. So, to integrate functions, okay? And this is already implemented in Python, okay? So we don't have to write a function to do that. This is actually pretty simple to do, right? But if we had the function already working, we don't have to worry. Okay, so far so good, yeah? So we're going to take our solution and look at the total population in that way, okay? We just have to come here. I just have to come here and take the solution and say, okay, our total population now, I just take, from scipy.integrate, I import this function called traps that calculates that using the trapezoidal rule. And what does this function want from you, right? It wants you to give it the points over here, right? And the distance between each point, okay? When you do that, you see, I have here the large U, the capital U over here. I just pass it the less population, okay? Just what I printed over here. Yeah, it's U minus 1, yeah, what is over here. And I ask it to integrate this, okay? And I got this large U here, okay? So this is a very small number because the population was going extinct, okay? And with that, then I can just think, okay, the population goes extinct when the total population is going to 0, and it's not going extinct when this total population doesn't go to 0, okay? Okay, so, and now we can just do a kind, it looks like a bifurcation diagram, but it's not, yeah, it is enough with a bifurcation diagram, yeah, I think it is, yeah, okay. And then we can just look at, as we change the value of L, what is the population size, the total population size like, okay? So once again, we are going to go for a range of values of L, okay? From here, I already cheated a bit. I put it is between 3 and 3.5, right? So we saw that 3 is going to extinction, 4 is not going to extinction, right? I'm going to stop at 3.5 here. And for each value of L, I'm going to solve the system with this value of L. Then I'm going to compute the total population size at the last time step. And then append this value to this list UU over here that I'm going to plot later, okay? Easy or not so easy? Yeah? Questions, comments? Yes? Mike, perhaps?
Can you show us the difference between the calculation of the integral using the trapezoid rule and the, I don't know,
the rectangles?
Yeah.
Ah, okay. So, so the other thing you could do here is you could say, okay, just print U minus 1, okay, summing all the values, and multiply this by delta x, that is L divided by m plus 1. Yeah. So not so much in this case, but in this case, this is not a very good, because these solutions are almost constant, right? So there's not going to be a lot of difference anyway, right? But if I had, for instance, like put 3.5 over here, okay? So since we are trying to do for 3.5 over there, just to check that this in fact is not going to extinction, right? Over here. Yeah, it's still pretty close, yeah. So depends Yeah, it depends on the function that you have. It's not so different. Yeah.
I was just gonna comment that maybe a difference is gonna be more clear if you have a very ugly function, something that is,
Yeah, yeah. Yeah.
but something that is just like something, just
Yeah.
something that grows and then goes down like this is
Yeah.
just fine.
Yeah. It also depends on the number of points you have here, right? So this is now if there's also already a 100 points, right? So this is pretty very finely spaced already. So this is not too bad, okay? But in general, it's always better to already go for the for the better one, okay? But this is not so. This is not terrible, you know. It's just that this is better. So it's, you know, yeah. Okay. So let's do this, yeah? So let's do this, so let's try and see what happens here. So you see, as a function of L, so from L going from 3 to 3.5, you see that population is increasing, okay? Here I plot in a log scale, right? So maybe let's plot first in a linear scale to see what it happens, right? So you see that the total population is increasing over here, but then somewhere around 3.1 something, it starts to grow, you see? But then there's an issue here, right? That is a little bit complicated. That is, over here, is it that I didn't wait long enough time? Or is it that I'm stopping at a very small population size, but not going to 0? So it's really hard to know exactly what is this value, right? Because it would be that I'm running for too little time and so on, right? So you have to try to refine this, okay? I won't go into too many detail over here, but maybe we increase the precision of the simulation, increasing the number of points. We can start with a smaller population, so it starts with 10 to minus 4. I know that if the total population at the end is higher than 10 to minus 4, or 3 times 10 to minus 4, then probably the population grew to reach there, right? So the population is not going extinct, okay? And then I use also a large time, okay? A very large time, yeah? So with that, now instead of looking at 3 to 3.5 that I already know that is between 3.1 and 3.2, okay? So I just go from 3.1 to 3.2, okay? In smaller steps, okay? And then let's run this, and then I'll plot this, but now I'm plotting a log scale, okay? Now you see it's taking longer because now I have more points, I have much longer times, okay? So it takes longer. Let's see what happens here. Yeah. And you see here you have a lot of 10 to minus 11, so this should all be numerical noise, okay? So this is extinction. But now here, a little bit over 3.14, the population is not 0 anymore. You see, it is small here, but not 0, you see? So yeah, so this critical pet size should be maybe a little bit over 3.14 or something like that, yeah? Okay? Are you convinced by that, yeah? Okay, so actually this is a calculation that we can do analytically, right? So I'm not going to tell you how, but this is actually, this should actually be equal to pi, okay? the critical pet size is pi. How comes the pi appears here, okay? So this is another mystery of mathematics, okay? Yeah. But then you have this general expression for this problem. We can calculate this as pi times the square root of g over r. We chose g and r both equal to 1, right? So this is just pi here, you see? Interesting, yeah? Interesting. Okay? Yeah, so this means that if I have a patch that is smaller than pi in size, we will have extinction. If it is larger than pi, we'll have persistence. And of course, if L is very close to pi, okay, the population density will be small, okay? It won't be all that large, okay? You see that the carrying capacity was 10 in density, so total population would reach something like 30 or close to 30, okay? But it doesn't. It doesn't grow as much as it would because it's leaking a lot of population, okay? Questions, comments? No? Okay, did anybody realize that I cheated in the methods odds somehow over here? That this odds is not what we used on Friday? Yeah, so let's talk about this, okay? So, in the last class, right, so you remember that I told you something along these lines, okay? So, yeah, so you see, this stuff here is a bit tricky, right? So you remember then when we talked about boundary conditions, right? And we have here, we have n points, okay? N points. So if I say that, I don't know, n is equal to 5, okay? N equals to 5. Okay, so I have 5 points, okay? And you remember that I told you that, okay, the delta x, or the dx that I have in my program, is going to be what? It's going to be 4, not 5, okay? Because I have 5 points that define 4 spaces between them, yeah? So what should be the dx that appears over there? Is L divided by n plus minus 1, yeah? But then if you look at my code for today, right, it's not n minus 1, right? You see, it's n plus 1, right? Why is that? Why is that? Yeah, so the idea is that if you look at this, at these solutions here, right, so let's go back to the, to the initial thing here. If you look at the solutions, right, so let's go to the top over here, okay? And then let me use not so many n's here, and L equals to, let me put it equal to 4. 4 is okay. Okay, you see here my dx here is L divided by n plus 1. This is a bit weird, but let's see. So, you see, remember that the boundary conditions here should be 0, right? So, the first element should be 0 and the last element should be 0. But that's not really what happens, you see? Yeah, so let me also plot this here, all right? So, oops, over here. You see? So, you see, I told you that at the boundaries, the population should be, the density should go to 0, okay? But in my solution here, it's not going to 0. So the first point and the last points are not 0, you see? Yeah? Okay? So what is going on here? What is going on is that actually, I did that trick of saying, okay, it is as if there's another point here, right? That is equal to 0, okay? So this is u at x equals 0 equals 0, and this another one here that is u at x equal L. This guy is also equal to 0, okay? So I have these 2 other points over here, okay? So my solution, I cannot really change these points because these points are already determined by the boundary conditions. So I cannot solve them over time. I just solve the points in the interior region, yeah? Okay? Okay, so this means that my solution doesn't include the 2 endpoints, just the middle points. That's why they don't go to 0 at the borders, you see? Because I'm only looking at them not from 0 to L, but from dx until L minus dx, right? And how many intervals I have here now? I have n minus 1 in the middle, plus 1 here, plus another 1 here. This is n plus 1, not n minus 1. Yeah? So this is a bit tricky, but yeah, it works like that. Yeah? Okay? And if you want to plot the solution actually not from starting at dx and stopping at L minus dx, you have to take your solution at the end and include a new column that says, well, all these points are 0 here, so the left points are 0, and the right points, another column with only zeros at the right-hand side as well. Okay? Yeah, makes sense. Do you feel too bad that I cheated a bit or not so much? Yeah? Okay, good. So I'll keep doing that then. Yeah? Okay, okay. Good. Questions, comments? Okay, so let's go for, now that we don't have any more problems with partial differential equations, then let's try to do another one. How about that? So the idea now, so let me use another notebook here. So the idea now is we want to go back to that, you remember that last week we were talking about models for populations with age structure, yeah? And we had what? We have something that was discrete in time and also discrete in, of course, yeah, if it is discrete in time, it also has to be discrete in terms of the description of the population, right? So we had newborn individuals, individuals of, at the year 0, individuals of the first year, of the second year, of the third year. I don't think we have gone too many years, right? So, but anyway, and then the time advanced 1 year at a time. So all individuals in the first year would go to the second year, and so on and so on. We had that matrix recurrence, yeah? We had that, right? So, but now I want to do something that is similar to that, but I don't want the time to be discrete. I want the time to be continuous, yeah? Okay, so I want to work with ordinary differential equations, not with discrete equations, with recurrence equations, right? So how we would go like to, how would we try to do that, right? So the way it would be like, starting with, again, with individuals of newborns, first year, second year, and so on and so on, right? So we would write something like this. So we have individuals of the first year, maybe we have a birth rate over here. Yeah, I should change over here. Yeah, so something like this. You have birth, you can have a death rate, like this, and you have what? You have individuals maturing into the next class. Okay, I have an equation for individuals of the first year, and the individuals of the second year, and so on. Okay. Yeah, and then this is the individuals maturing here is going to be proportional to the number of individuals that are in this class, right? But then I can put something like this, okay? And these guys here are going to show up down here, okay? So these are the individuals that left this age class and entered this age class, okay? But now I ask you, what should be the value of m? Suppose that I'm measuring time, so my t is measured in days, okay? In days, okay? And 0, 1, and 0, and 1, etc. is 0th year, first year, etc. All right? So what should be this rate here? What should be the value of this rate? Well, the inverse of this rate should be the average time that it takes for individuals here to move here, okay? So 1 over m should be equal to 1 year, yeah? Yeah? But I'm measuring time in days, right? So 1 year is actually 365 days. And then in these units here, I have to use m equals to 1 over 365. Yeah? Makes sense? Okay, good. And now the other equations are more or less simple, right? Because I only have birth at the first one, and then I have only death and maturation, yeah, and aging, yes.
I'm sorry, I don't know if I'm not following correctly, but the thing about using time t in days and then the populations are in years and we're just using 1 over 365. Like if 1 day passes the population N0 is going to decrease. And then the rate is not going to be 1/365 anymore, right? Because
yeah, but this is the average. Okay, so you see, after 1 day, some of the population already moved here, and then after another day, another fraction. When you wait for a long time, the average. So you see, if you didn't have any, if you just have this equation over here, like something like this. Let me put it in this way, right? So if I have this thing here, okay, just this, okay. What is the solution for this? It's an exponential, okay. I have the initial population here. This decreases exponentially, okay, goes to 0. But how long, in average, does it take for an individual to live? 1/n, okay? But you have individuals living much quicker than that, and others taking much longer than that, okay? So the average is something, this is time over here, right? And the average, 1/n, is around here, okay? So you see, it's already a bit funny, right? Because in our discrete model, it was very precise, right? So individuals took 1 year to move from this class to the other class, right? And exactly 1 year, okay? But now, you see, even if this average is correct, some individuals just age faster than others. Yeah, this is weird. Yeah, this is weird. Okay, so let's see. So, yeah, so I'm already have the feeling here that it's not going to be so good, this model, yeah? Okay, so let's see that in the computer, right? But first let me finish writing this, right? So I'll have here mortality for population 1, and aging, and so on, right? So M1 and 1 minus G2 and 2 minus M2 and 2, and so on, right? And of course, I have to stop somewhere, okay? I don't want to go to infinity here. I will stop at some G, M, M, dt, but the equation is going to be exactly the same, right? So I have M, 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 M minus 1, right? The previous one minus the mortality of the last class, and I don't have it aging into the last, into a different compartment, okay? So I have a system of m plus 1 equations, but they're pretty simple, right? So you only have birth in the first one, and this birth, I will talk this only much later, okay? But now I want to see what happens just due to aging, okay? Just due to aging. So what I'm going to do is, perhaps we would turn off mortality, and we would also turn off birth, okay? And we can look just at what happens due to aging, okay? This passing of time when populations, yeah, you just have movement across different age classes. Okay, so let's see how do you do that in the computer. Okay, so over here, let me turn this off. Okay, so here is more or less what I just told you. Okay. Okay. And now, okay, let's put only 7 classes. Okay, only going for N6. So there are 0. So these are 7 classes. And now I asked this as an exercise. Okay, so do you have time for that? Do you want to try to implement this or not? Are you feeling Monday is a day full of energy, or Monday is a lazy day where you're still not fully energized for work? What do you think?
Fully energized.
Sorry?
Fully energized.
Fully recharged. Nice. Yeah. So some 15 minutes there to try to write down this stuff here. Yeah. Yeah, I think your colleagues already hate you now, yeah? Yes or no? Let's try to do this. This is not very difficult, right? So we just have to, for each class, you have to sum. I already have here the first line where I just take the mortality, okay? I just take the mortality here, so this is minus g times x. Now I have to sum to each of them the previous age less times m, and I have to take out from each of them m times themselves, okay? So this is how it is here in the board, yeah? So I have, I asked you to ignore birth for now. You just have for each equation to sum m times the previous, the population of the previous age less, and minus m, there's no m, m is just a constant, yeah? Okay, so yeah, I don't need this, so yeah. Aging is the same for all ages, yeah? Okay, so I just have to subtract the aging term for each population, for each age less, and sum the aging of the previous age less. Yeah, this is not, shouldn't be too hard. Let's try to do that. Let's try to do that. So we have here, so let me start with, I will run this. I don't know if this is going to give me an error because of this. Perhaps not. But let's do it step by step, right? So what do we have here, right? So we have that G, the mortality rate or the death rate, it could be different for each x, okay? So I have D0, D1, D2, up to D6, okay? So the number of points here is 7, right? As I asked you to go from 0 to 6, including 6, okay? So there are 7 points. I'm putting the birth to 0. My rate here of maturing here is 1/365, as we discussed. I'm putting all the mortalities to 0 except the last one, so that I don't accumulate population at the last one, right? So just that individuals in the last age classes are actually going to die eventually. Okay? But let me, before trying to solve this, okay, let me just look at what is x, right? So x is an array with 7 values, okay? X0, sorry, X0. It's an array with 7 values. I just set the initial condition for it to have 100 individuals in the first age class and 0 in all of the others, okay? Then what is going to happen here, okay? So I'm writing the derivative of this, right? It's going to be, so looking at the equation, right? So minus g, so instead of, I didn't write it here, right? So instead of writing like this, yeah, no, it's okay like this. So for each of them, I have g times itself minus m times itself, right? But then I don't have this term minus m times itself in the last equation, you see? So I have to just subtract minus m times x itself for all the equations except the last one, right? Yeah, so how do I do this? I take this dx here and I subtract what? I subtract m times s. But I don't want to do this for all of the s. I want to exclude the last one, right? So how do I exclude the last one? I take all of the elements except the last one, okay? Both here and here, yeah? Okay? So you remember how, yeah, so if I take this except the last one, yeah, I go, what is this slice here, right? So I take all of the elements up to, but not including this one. What is this one? The last one. Okay, so this here has one last element. You see? 1, 2, 3, 4, 5, 6. It's not 7. You see? I excluded the last one. Okay? So I do this. So I subtract m times x for all of the equations, right? And now I want to sum to all of the equations except for the first one. Except for the first one, I'm going to subtract I'm going to sum m times the previous one. Yeah? Okay? So what do I do? So this is similar to what we have done in the last class, okay, to solve the diffusion equation. I'm going to say that gx, starting from the second one, I'm going to sum, okay, this minus 0 plus 0, you know what it is, right? So this is, I'm telling that gx is going to be exactly what it was before, minus this stuff here. And here I'm saying gx is going to be what it was before, plus what is here? What is this here? This is m times x going up to the last one, right? So let me delete over here. So what is this, right? So this array here starts, so these are the derivatives starting with the second element. And in the right hand side, these are all of them starting from the first and going and excluding the last one, right? So these are shifted. Yeah? So I'm summing x0 to gx1, summing x1 to gx2, and so on. Yeah. So let me try an example here. So maybe arrange seats over here. You remember this? So I have the whole of x here. If I have this here and this here, okay. You see, here I get out the first element, and here I get out the last element, right? And what I'm writing here is that I'm summing to the ones starting from the second, the ones that I get the last one out. So I'm taking these ones here and summing the previous ones. Yeah. So just like I had in my equation, right? I have for each equation I have a positive term that is m times the population of the previous age class. Okay? Does that make sense? Okay, so and so that's it, right? So I would still have to include birth, right? In the equations here I had birth only for the first class, okay? So I can take the first class, that is gx0, and sum birth, okay? But the birth rate, okay? I'm not going to use this now because I'm just going to put b equals to 0, but okay. It would be something like this, okay? And now I can actually solve my equations, okay? With some lucky this works, okay? Maybe, yeah? So let's plot this, okay? So this is what's going on, okay? It starts with 100 individuals for the 0 class, okay? Newborns. And all of the others are individuals for the first one, first year, second year, third year, and so on to the 6th year, okay? And you see that the first to increase are, and now I've done something to make our lives easier. That is, t here was measured in years, okay? So I have here t in days, okay? So I had here 365 times 10, that is run for 10 years, right? Yeah, 10 years. But now when I'm writing this scale here, I divided t by 365, so that this t that appears here is actually in years, not in days, right? Just so that we can see more easily what's going on, okay? Yeah? Okay, so this goes down, okay? The newborns are maturing into the second year, then third year, and so on, okay? And these others go up in the order, right? First the first years, then the second years, then the third years, and so on, right? But as we had already talked about, this is not really a very good approximation for this problem, because you see, by the time I finish here the first year, so let me just limit here the solution to the for the first 2 years only, okay? You see, by the end of the first year, there is still almost half of the population is still in the 0 year, okay? But and at the end of the first year, there are a lot of individuals in the second year, in the third year, in the fourth year, you see? So it's not that nice, right? Yeah? Yeah? So you see, there are individuals that are running ahead, there are individuals that are staying behind. It's a weird aging thing, yeah? Okay? Okay, so this is weird, right? This is weird, right? It means that my model doesn't actually do what I wanted it to do, yeah? Okay? Okay, but then I promise you that this will get better, okay? So, do you have questions so far? Yes?
Can you go over the function again? Because I didn't understand how you build it.
Okay, so the aging function over here. Okay,
Yes.
so I defined a new variable that will be the right-hand side, the derivatives. And I said, okay, for each class I have that the derivative that includes a terms that is mortality times x minus mortality times x. Then I subtract from it minus the maturation rate, but for all the classes except for the last one. Okay, so far so good. I don't subtract this term for the last one because the last one doesn't have this minus m times n over here, you see? It doesn't age into another class, okay? So the last equation doesn't have this term here that the others have, okay? Okay, and then now I want you to include to sum these terms here, okay? These terms here. You see that the first population doesn't have a term like that, okay? Only from the second onwards. And from the second onwards, what I sum to it is not itself, but is the array shifted by 1, right? So in the first equation, in the n1 I sum n0, in this n2 I sum n1, n3 I sum n2, right? So I sum. What I'm looking at is I take the array of the derivatives here, getting out the first. Okay, so this starts with n1, n2, and so on, and I sum to it the array of n's starting at 0. You see, so I sum n0, n1, n2, you see? So this is what I'm doing here. So I'm taking this dx starting at the second value, I'm summing to it the value of x times n, starting at the first value. See, so when I have just this 2 dots over here, I start at the first value, but I have to stop. I cannot go to the last value, right? Because the last value is not summed to anything, right? So in the last equation appears the penultimate value, okay? So not the last one, you see? Is it clear now? Yeah, so it's pretty much like the last time, okay? But then it was a little bit confusing for the diffusion equation. It's still a little bit confusing here, I guess. Yeah, so this working with shifted arrays, okay, so
isn't it supposed in the above equation the dx that goes until the
sorry,
the second line of dx?
Yeah.
Yes. Why is it also x?
Yeah, because this
1?
is aligned here, right? So for the derivative of n1 has minus m times n1 itself.
Yes.
Yeah. So
Shouldn't
to the first element of here, I subtract the first element of x, second element here, second element of x, and so on. Right. So they're still aligned. I took out the last element of both of them, so they are still aligned. Here I misaligned them by taking out the first element of one and the last element of the other. So now they are shifted.
Okay.
You see?
Mm-hmm. Yes.
Yeah. If I take exactly the same elements from both, okay, I'm taking that out, but I'm not shifting them. Okay. Okay. More questions? Okay. So we see this is not so nice. Okay. So, but then what I want to do is, okay, maybe if we instead of having large age classes that have large bins, this problem would probably be lessened if I had a lot of shorter time bins, right? Because instead of going from 0 directly to 1 year, okay, maybe if I had a lot of age bins, right? So I had to go from 0 to 1 year, I have to go from 0 to 1 month, then 1 to 2 months, then 2 months to 3 months, 3 months to 4 months, and so on and so on. Okay, I have to go over all of them. Okay, and this in fact happens. Okay, so if I instead of going with these large age beings, if I have a lot of small age beings, this problem that I just described here of having a lot of population still here after 1 year and so on, okay, this is usually gets better as I decrease the size of the age being, okay? And what is the goal here? The goal is to pass this to the continuum, okay, to have a continuous age distribution, okay? So pretty much like we did with space, instead of having just a few patches, we're going to fill the space with many very small subdivisions, right? And we are doing here this now with age, okay? And what would the age equation look like now, right? So I have now, if I look at a certain age, of age class I, right? I have the mortality, I have the aging, that is proportional to NI, and I have, oh, there's an error over here. Yeah, this is minus, not, yeah, like this. Yeah, this is, yeah, like this, okay? So I have individuals coming from the previous age class, okay? But now I want this I to actually correspond to an age S, okay? It's an age S. And then I'm saying, okay, the age S is I times delta X. Delta X is, so for instance, I had here, I was doing from 0 to M, I was doing from here from 0 to 6 years, okay? 6 years. With 7 points, I had age beings of 1 year each, okay? If now I have, instead of 7 points, I had, I don't know, 70 points, okay? I would have that each age being would be 1 over 10 years. Yeah, only 36 days for each age being. Yeah? Okay? So, so the age x to which the ni represents is I times delta x, okay? And we then write these equations. Maybe I should do this on the board, but I think this are very simple steps. Let's try to do without the board, yeah, because we are running late, yeah. So you see the differential equation for each age that now I represent as gn of x, okay, gn, so the population at age x is going to be gi, that is the death rate of the age x times nx itself, minus the population of nx itself, plus m times the population of the previous age class, okay? What is the age of the previous age class is x minus delta x, right? Yeah? Okay. What do we do now? We want to take the limit of very, very small age classes, okay? For delta x going to 0, okay? So I'm going to rewrite my equation here, putting this delta x into evidence, okay? Then I write this down, I can factor out the m here, okay? From these two terms, and I want to also factor out delta x, okay? And then I get this expression here, okay? And what happens with m times delta x, okay? You remember here that, so let me go to the board just to remember this stuff here. So remember here that this 1 over 365, what was it? It was 1 over 365 because the length of each age being was 365 days, okay? So if I have a being size here, or the length of each age class, I don't know, something like 30 days, so m is going to be 1 over 30, yeah? So you see, this m here is proportional to the length of the age class, yeah? Or inversely proportional, yeah? Okay? So m times delta x is actually going to be a constant, okay? Okay, so, and so with this, now let me go back to the equations here. So with this, we have that as delta x goes to 0, the expression in parentheses over here, you see, is exactly what? Is the definition of the derivative of n with respect to x, okay? And now I can think of n as a function of both x and t, and then I have to use partial derivatives, okay, because n now is a function of two variables, but I have pretty much what I had before, right? So this is del n del t equals to minus g times n minus, and I tell n times delta x here, v, okay, v times del n del x, okay? What is this v here? It's just this m times delta x, and this v should be exactly 1. This is the rate of aging, okay? If I'm measuring age and time in the same units, they are both in years or they're both in days, v should be how many years you age per year. This is just 1, right? Yeah? Yeah? Okay, anyone ages faster or slower? I don't know. Yeah? So you age 1 year per year, right? So this is just 1, okay? I just included v here because depending on units, okay, you could have a different value if you measure age and time in different units, okay? But usually this is just 1, okay? Good, people. Yeah? So what we have here is a new kind of differential equation, okay? This is called an advection equation, okay? And this term here is the mortality term, and this here is the advection term, okay? And what does this do to my population? It makes it grow older, okay? It makes it age, right? It moves the distribution of the population towards larger ages, okay? Hopefully without changing them too much, right? So let's try to solve this, okay? Let's try to solve this. So the numerical implementation is pretty much the same as before, okay? I excluded here the birth because I don't want to talk about birth right now, okay? And the equation is pretty much the same. The only difference is that instead of having the n here, I substituted n by v over dx, okay? V over dx. That is exactly the definition of v, okay? So v is m times dx, so m is v over delta x, okay? Okay, so yeah, I'm changing also, I'm using n instead of x here because x now is the age, right? So not my, yeah? Now I'm going to use 100 points here for the same range of ages, you see from 0 to 6 years, okay? I don't need this at all, okay? No birth. And once again, I don't want to have any birth or any death except at the last class, okay? And I'm going to see how it happens with the initial population of 100 for newborns, and let's see what happens with this population, okay? Here we go. Yeah, okay. And now if I plot this, well, this is weird, right? Yeah? Let's maybe look at only a small region of this, right? So maybe from 0 to 2 years only, okay? The problem is that there are too many lines, right? But you see now that if you look just for the, yeah, let me do something better here. So let me plot just the first column, okay? The first column is individuals of age 0, okay? Individuals of age 0. So you see, they go to 0 much faster than before, you see? So before, when we had this here, after 4 years, the population wasn't 0 yet, you see? For the first age class, okay? Now it goes to 0 much faster, okay? You see, so you see that using smaller age beings is helping this problem, okay? So it is still not immediately going to 0, okay? But it's going to 0 much faster, okay? And then when you have more age classes, of course the second age class increases and then decreases, the third one increases, then decreases, and so on, okay? if these were perfect, right? So you should see all of them going up, and then the one going up, and the second going down, and the first going up, and the fourth going. Yeah, you see, but this is not exactly what happens. But this is an approximation that gets better as delta x gets smaller. Okay, if I put double the number of points over here, this gets better. You see, so you see that it goes up and down quickly, more quickly. You see. So, you see, yeah, makes sense? Okay, the fact is that here, okay, I'm using, I'm still solving, this is still called the method of lines, as we use it for reaction diffusion equations. But it turns out that for these advection equations, the method of lines is not so great, okay? So, there are better methods that capture better this, you see this characteristic of the population of moving to the right. You see all of them. So what you would expect, right? Let me show this on the board very quickly. So the solution. Yeah, no. Let me plot the animation first. Sorry, kind of confused today. So let me plot the animation first, okay? Just to see what this looks like, okay? So I think this takes a little bit. Yeah, I think it takes a lot of time to render this actually. So let me show in the boards what it looks like usually. Okay, so so you see what do you expect? If you have a population distribution that is like this, okay, this is x, the age, and this is population density, okay. What you expect? If you don't have any births, right, after some time, this will just move to the right, okay? If you don't have mortality as well, this moves to the right. So this is the solution to the advection equation. The population keeps moving to the right, right? So since this method of lines is not very good, right, it tends to, with the passage of time, it tends to spread out a bit, okay? So if I had a better numerical method, I wouldn't see it spreading out, okay? I would see the shape being very close to the original one and just moving to the right. So this is what the original partial differential equation does, right? But the numerical method here, I had to use a very large number of subdivisions here to see this happen, okay? So let's see if the animation worked. Yeah. Well, here it is, right? So let's start from the beginning. So you see my initial condition here is with a very sharp, I didn't help it much, right? So I put a very sharp initial condition, yeah? And then it goes to the right, but it's spreading a bit, okay? So this is actually a numerical error, okay? Because the equation itself should keep the shape of this intact, and it just goes to the right. So to make a better approximation, I have to use a much larger number of points over here, okay? Okay, so I'm showing you a numerical method that is not so good, but you can get some sense of what this equation does, okay? I don't want to go into the appropriate methods for this particular kind of equation, okay? Okay, questions? Does it make sense, people? Yeah? I think we are running, yeah, we're running late already. At the end here, I thought a bit about what do you do with the newborns, okay? And then you have to introduce a boundary condition, that is, what happens at age 0, okay? Age 0 are going to have to be the newborns, okay? And what do? You just multiply for each age class. You have what is called a maternity function, that is the number of newborns of individuals with that age, okay? And then I sum this over all age classes, or I integrate over all age classes, and this is going to be my number of newborns, and then I have to sum over here, you see, so I take this b here is the number of newborns here, integrate b times m, and I sum this to the flux, to the number of individuals getting into the first equation. And you see that once again, this boundary condition not really just like in the reaction diffusion equation. Okay, I don't have in my equation the newborns themselves. I have the first, actually the second age. Okay, not the newborn, because the newborn is a number. I don't follow the numbers in time. This number is given. I don't solve this with differential equations, right? It is a given number. I just follow this from the second age class. Okay. It's kind of tricky, but okay. But yeah. Questions, comments. I know this was a bit rushed, perhaps, but yeah. But maybe we still have a few minutes for comments or something like that. So I wanted to show you this, right? Because of course now we have an idea of what an advection term does. Okay, so the advection term is a term that looks like this, right? Where you have this del n dt, and you have just the first derivative in space. Okay, oops. Only the first derivative in space, and of course, you can combine this with diffusion. For instance, if you have directed movement, so you can use this also for movement in space. You can use this for a lot of different stuff. Okay, so whenever you have populations going into a certain direction with a given velocity. Okay, so and this velocity would be in space, it would be in age structure, could be in physiological structure. For instance, if you have individuals that grow with time. So if, for instance, when you model those fish that start this size and then grows to be several meters of length. Okay, so they grow with time, and you say, okay, this velocity that I included there could change according to the size of the fish. So you would see the fishes of different sizes. And of course, this growth rate eventually saturates, right? So it eventually goes to zero, because at some point they stop growing. Okay. So there are all kinds of different modeling approaches that uses this kind of idea. Okay. So I want to, give you a taste of what it looks like. Okay. Questions, comments? Okay. So tomorrow is our last class. Okay. Yeah. I'm kind of in doubt of if I go back to this or if you want something else, or do you want me to talk about something particular, or